The other thing we need to consider about nuclear power are some of the safety issues, and the reason for that, we kind of alluded to one of the aspects earlier. Um, Two reasons. The one is the high energies, and the other is radioactive material. Because of those issues, we tend to see that nuclear power stations have a far more need for safety mechanisms in order to make sure that nothing goes wrong. Because if something does go wrong with a nuclear power station, it's likely to be a bigger issue than it would be with a say a coal-fired power station. And so, like I say, there's fairly significant safety measures involved, and as a result, because of those significant safety measures, it generally means that nuclear power stations are really quite safe. And generally speaking, if there is an issue, it's not because of something going wrong necessarily. It's say because of, if you think about Fukushima, it was because of a natural disaster. It's not often these days that it's a problem with the reactor itself. So looking at the diagram, the first one that we'll have a look at is the reactor vessel. So the reactor vessel is what the reactor is actually contained in, and it's usually made of thick steel. And a couple of reasons for that. The first is that it withstands the high temperatures and pressures. So the internal energies that we're talking about here are quite high, and so the pressure of any gases in the vessel can also get quite high. The second thing is that it can absorb alpha and beta radiation. So any of the radioactive material that does end up in there, any stray alpha and beta radiation that escapes will often just be absorbed by the reactor vessel itself, and can also some gamma rays and stray neutrons can also be stopped as well. So there's sort of the first layer of safety. The second then will be if we look at, we've got the reactor vessel, so that's this part here. We've then got that larger layer outside, which is basically the containment building itself. So the reactor vessel itself is now housed within a thick concrete container. So we've kind of got two layers here. The main reason for the thick concrete is that it will absorb any other neutrons that do happen to make their way out of the vessel. So it absorbs neutrons and some gamma rays as well. So two layers around the reactor itself that will help to shield any radiation that might be coming out of the reactor. The third one is the emergency safety mechanisms. And so when we talk about emergency safety mechanisms, we're talking about things like the control rods being automatically inserted into the reactor, and that those emergency safety mechanisms will quickly shut down the reactor. And again, that's in the case of accidents or emergencies. And when we talk about accidents here, it's usually going to be accidents that are not so much from what's happening in the reactor itself, but some external factor. And the fourth one is that the fuel rods themselves are usually inserted and removed robotically. So that means that we don't have to have people anywhere near material that's got some fairly active radioactive substances in it, and that, like I say, reduces human exposure. To radiation. So they're the safety aspects of the reactor itself. There are a couple of other sort of further considerations that need to be taken into account, and that's when we start looking at what happens with the spent fuel rods. So once they've been used and the fuel source is no longer viable, they have to be removed, and along with other nuclear waste, so the moderators and the control rods themselves, those substances tend to be radioactive, given the all of the fission processes and all of the unstable nuclei that are often produced, and so they must be disposed of appropriately. And once they're disposed, it's not just a matter of disposing of them, there's an issue of storage there as well. And they need to be stored separately from biological material. So we don't want to have radiation anywhere near anything biological, and in particular, when we talk about anything biological, we're really talking about the food chain. So we don't want to have it anywhere near any organisms that can be consumed by other organisms. Finally, the last thing, as well as looking at the nuclear fuel and nuclear waste, any power station has a limited lifespan. The technology that's used will eventually be superseded, or even just with wear and tear will need to be replaced. So usually the lifespan of a nuclear power station would be somewhere in the 25 to 50 year lifetime or lifespan. And so after it's the nuclear power station has done its job, it would then need to be decommissioned. By decommissioned, we're basically saying that it needs to, everything that was used in the power station itself has to be removed. So removing the fuel rods and other waste. So again, other waste being control rods, moderators, and any other waste products that are produced. So the water itself, the heavy water, or the water that's being used in the heat exchanger, and the reactor itself is enclosed in a larger concrete shield, and the purpose of that is to basically allow any radioactive material there that's still in the power plant itself or in the reactor itself to basically to decay over a fair amount of time. So it's left alone then until its radioactivity drops to background levels. And in some cases that will probably be sort of somewhere in the vicinity of a century, so 100 years later, and you might then be able to go back and reclaim that land and either put another power station in there or use it for other purposes. So they're the safety issues with nuclear power, and all fairly significant things that do need to be taken into account. But ultimately, the amount of energy that can be produced, it does mean that these negative aspects they're important, don't get me wrong, but the energy that can be produced is often far outweighs some of these other concerns that need to be taken into account.